So are there any questions so far? Okay, so if not, let's try to start from some, let's see, how far do I need to say? Hope I can finish it. So let's start from something that's very simple, like, some kind of definition of what is probability. So suppose we have a space of events, let's call it capital omega. It is basically a set of events, and any point of that set is just an element. Let's use omega to denote it. Okay, so that means you have various different kind of event, and then we can put some condition that there's a subset lambda, which is basically a subset of our events. That's a subset of omega, and the probability of the event lambda that belongs to this set of lambda is actually, if I just draw it pictorially, which is quite easy to understand. It's just like that. Okay, and here NT, the right hand side is more like a mathematical description about what I'm trying to say, and NT is the number of trials. Okay, so basically you just sample or try to pick up the element NT times, and you ask how many times I will get the element that is from this subset lambda, and the ratio of this number where we got a element that is in the subset lambda with the number of trials at the limit where the number of trials goes to infinity is the probability of that subset. Okay, so so now I'm going to say a little bit more about the case where we have multiple random variables. So for the case of multiple random variables, there are some important concepts that I need to discuss. One is the joint probability. That is denoted by PAB. It just means the probability that event A happened and event B happened. So to some extent, it's the probability that of a subset that is the union of set A and set B. Okay. So I'll try to use a simple diagram to understand that again. So suppose here is our event space for every possible event, and this circle represents the event A, and this triangle represents the event B. Let me try to make sure that this is event B. Okay. So in the middle is basically the case that you have A belongs to A and event B belongs to B. Okay. And you can also label other regimes if you want to, but I'll just skip that because it should be relatively simple. So if I try to write it in this way, then the probability, the joint probability of PAB is just the ratio of this thing with omega. Okay. So that's like the first idea, the joint probability. And the second one is that I want to define another probability, which is the marginal probability. That is basically we consider the joint probability PAB, but we sum over all the possible scenario for the event B, which means that we ignore some of the conditions. Okay, so let me try to make this example more specific. So suppose the event space omega is something related to, you know, I just randomly write something. And suppose that's the event space. And wait. And A is like the character is red, and B is like the number is even. Okay. So the complement of A, it just means that the character is blue, because in our event space we have blue numbers and red numbers. And the set B or the criteria B is saying that we ask whether the number is an even number or it is an odd number. Okay. So in the previous case, when we are talking about joint probability, we can ask the question like, what is the probability that we have a red odd number? Okay. Or we can ask like, what is the probability to have a red even number? Sorry. Or we can ask the question in other kind of combinations. So, what is the meaning of this expression is saying that we are trying to ask the question more like, we ignore whether the number is even or odd. We just ask whether the character is red or blue. So you first figure out what is the probability that you have a red even number, and then you figure out what is the probability you have the red odd number, and then you add them together, then you eventually get the probability of a red character. Okay, so that's very simple. So why I'm talking about that? Because it is going to be a useful expression for our later derivation. But also from the joint probability, I forgot to mention one thing, which is also very important, but it's probably too trivial to mention. That is, if you consider all the possible scenario for joint probability, it needs to be sum up equal to 1, because that's the normalization condition for your probability. Okay. So are there questions you want to ask? Okay. If not, I'll just continue. Okay. So let's see. Okay, so one question is, suppose we have this expression in formula. Can I try to understand that in diagrams? Actually, yes. And the answer is that because all you care is about whether A is in this circle, and the total event that you think about is the total event space. So that's the expression for this marginal probability of A. Okay, good. So another important condition concept for multiple random variables is the conditional probability. Okay, and during these 2 years, this concept is extremely important, because we know that there are two events, whether you got a COVID or not, and the other possible probability description is that whether your test is really works or it has some fallacies. Okay, so that's basically related to this idea of conditional probability. So the conditional probability of B given A is observed is denoted by this notation. Okay, and from the diagram, it is relatively easy to develop some intuitive intuitive understanding. So the probability of B given condition A actually can be understood by this diagram. Okay, because you give the condition A, that means that it needs to be within this circle, and you are asking what is the probability that you get something that's of B. So you need to find the overlap, which is this shaded region, and divide it by this event space of A. And similarly, you can simply guess or derive that this is the conditional probability of A given B is observed. Okay. So another relatively simple observation is that the joint probability of AB is equivalent to joint probability of BA. That's because the union is basically a commuting operation. So we can ask what that is, and as we already draw, this thing is basically where it is here. This shaded region divided by event space omega. Okay. And we can try to build this expression with our conditional probability by divided by event space A, and then multiply somewhere. And from the diagrams, we understood that this is the conditional probability, and this is the marginal probability that we just derived here. Okay. And simply, you can also do the same trick, but now take B as the fictitious expression for your right-hand side. Then let's try to write down what these terms means. This is just probability conditional probability of A when B is given, and this is just the marginal probability of B. Okay, so we just derive this relation. And this is the Bayes theorem. Okay. So let's see. So now I'm going to write down an extended version of Bayes' theorem by, let's try to repeat what we just derived previously about this figure. Okay, this is A, and this is B, and this is the union of it. But now we can try to divide our event space into two parts. One is called omega 1, and the other is called omega 2. Okay, and this dividing of like the event space into different pieces is just quite arbitrary. I'm just trying to use the simplest example to illustrate what is the extended Bayes theorem. Okay, so the marginal probability B is basically this. This is basically from our previous definition, but I just replace A with B. Okay. The reason is that triangle is not symmetric about left and right, but circle is always symmetric. But anyway, that's not really important reasoning. So so now if we try to divide our event space by omega 1 and omega 2, then we can think of this expression by this expression. Let's try to consider the events within this omega 1 space, and then we divide it by the omega 1. Okay. And then again, we divide it and we multiply it and do it. Basically, we're not doing anything useful, but we can still do that. Okay. And so if we try to decompose our initial expression by this figure, it means that we still need to include the other part, that's basically the lower part of omega 2 into our expression. And that's also relatively simple. Okay. And if I try to write it down in terms of equations, it just means that this is the conditional probability of B given omega 1 times the probability of omega 1 given omega 2. Okay. So this is like a quite arbitrary, decomposition, and the general form of that is actually, you can write it in terms of arbitrary partitions. And you use that if we use that into the Bayes theorem by replacing this part, then we got the general form of our Bayes theorem. Okay. So so right now this omega I is choose to be quite arbitrary, but in fact we can make a specific choice. For example, if I choose omega 1 to be A and omega 2 to be not A, and this means not A, or the complement of A. Then we'll see that the probability or the conditional probability can actually be expressed by. So again, it is quite, we can try to understand what's in the denominator in an intuitive way. It just says that because in the denominator, it should be PB of B. And the origin of that is basically from the expression of this equation. You just divide the PB of B to the other side. And PB of B is, in our graphic notation, it is like this. And you can think of it as the intersection divided by A and A divided by omega plus the complement of it divided by the held omega divided by omega. And then eventually you'll find it is, what you're doing is actually doing this object. Okay. So that's one of the important ideas about conditional probabilities. So are there questions so far? Okay. So if not, I'm going to talk about the independent variables, which is another very important idea. So when we talk about the joint probability, that's probability of event A and B, we usually just write it as the, it's very tempting for us to write it in this way. Okay. So we said that the variable A and B are independent if this condition holds. Okay. So why, if this condition holds, it means it is independent random variables, because you can make a simple derivation about the joint probability, and from our previous derivation, it should have this relation, and if we have this condition for independent variables, we can re-express the joint probability by this expression. And you see that B dependence is completely gone. So, so the conditional probability of A given B is actually independent of B. So that's why we say A and B are independent random variables. So, so if we have, you know, multiple random variables, for example, let's try to take the case we have ABC random variables. And when we talk about independence, there are several definitions. One is the so-called mutual. Let me start from the simplest one. The simplest one is the pairwise independent. Okay. What do I mean by that? It just means that the joint probability of AB can be simply written as, and then for BC and CA, you basically have all the repeated structure. Okay, so that's for 3 random variables. You just pick 2 of them, like in a pairwise fashion. If they are pairwise independent, then you got this relation. So the other is called the mutual independent. In the previous case, if we try to calculate the joint probability of ABC, what mutual independent means is that you can basically write it as okay. So you can immediately see that pairwise independent is basically a subset of mutual independent. Okay, so to some extent, mutual independent is more independent than the pairwise independent. Okay. So one interesting question is try to construct the possible example for that, but I think I'll skip that on the course. So okay, so I think I'll just also mention some very basic idea about mean, variance, standard deviations. So mean is very simple. I think we already used that in several cases, but here I'll just write down the most general expression when we have a probability distribution. So mean just means that we are doing a weighted sum. according to the probability of a specific event. Okay, so that's basically the definition of the mean value or the expectation value. And the other important quantity is the nth moment. It's defined as the mean of the random variable raised to the power of n. Okay, so it just means that you have this thing, you take it to the power of n, but you still do the weighted average of this quantity. And the nth central moment just means that we are still calculate something that is like moment, but central in the sense that we are calculated with a reference point that's the mean of our random variable. We just raise it to the power of n. So if I write down the definition again, it looks like this. So a very special quantity is the second central moment. Or the variance. It's basically the square of this thing, and you can just simply expand it, and you'll find it is equivalent to the second moment divided by the square of your mean. Okay, and here sigma is usually called the, it's also called the standard deviation. And another quantity that I want to introduce is the correlation function when you have multiple random variables. Okay. So suppose you have random variables A, B. And you have some function f would take this random variable A and the function G, which you take the which map this random variable B to some value. F and G are also random to some extent. Then the correlation function of f and g basically is defined as like this. Okay, if I try to write it in a more formal way, it just means that I consider all the possible outcomes of event A and B, and we just evaluate the value of A and B, f and g with those events, and we times the probability or the joint probability of event A and B, and subtract the product of the means of f and the mean of g. Try to move it somewhere. Okay, so that's a definition for a correlation function for two random variables. So during the course, you might face several integrals, but one of the most important one is the Gaussian integral. I think I asked this question specifically in the survey, but I think I'll still try to do that again to make sure that everybody knows this thing exists. Okay, so the trick of doing this integral is basically try to square it. So suppose I try to write another g, but use the dummy variable y. Okay, and I time g with itself, then I'll basically have and after change of variable from xy to polar coordinate r theta, this thing will be related to wait, the theta is gone. Okay, and the theta is easy to evaluate. It's just 2 pi, and this rdr can be replaced by the r squared divided by 2. Okay, so eventually these two get killed. And then you'll get pi over a. Okay, and since we know g squared equal to pi over a, it just means that g is equal to square root of pi divided by a. So that's a very elementary integral, but it is nice to know this kind of formula exists. So even during the midterm exam, if you forgot it, you can still derive it. Okay. So that's one thing about this simple mathematical background. And the other important background for statistical physics is the Stirling's approximation. Okay. So Stirling's approximation is to ask the question, if I'm trying to evaluate n factorial, when n is large, what is the good way to approximate n factorial? Okay. So one important thing to evaluate n factorial is starting from the definition of it. If you know I think it is called the gamma function, if my memory is correct. This is basically the definition of n factorial if you try to write it in terms of the integral. Then you ask a question like, why do I want to do that? The reason is because of the following thing, that you can always exponentiate this power expression by exponential and nature log x. Okay. So this is exact. I'm not doing any approximation currently, but now I'll try to re-express it by this way. And now f of x is just n nature log x minus x. So I'm again doing nothing. I'm just collecting the exponents and try to say it is a function f of x. Okay. So so now we are going to use the idea of steepest descent. That is, we know this f of x now is has this functional form, and we can try to expand it around some specific value x bar. And if I'm doing that for general x bar, I expect the Taylor series to look like this. Okay. So at this moment, it's not clear that I can do that, but let's try to move on. So one of the idea for steepest descent method is that the integral is basically dominated by the point x bar, such that the first derivative of it is equal to 0. That corresponds to, if I just take this f of x and make the derivation, then we know x bar equal to n. Okay, so what's the advantage of doing that? Because if I take the second derivative of f of x, then I got when x bar equal to n, this thing is minus 1 over n. So this expression is good in a sense that if you put it here, you see that the coefficient goes like 1 over n to some extent. So when n is really large, so large that this vector can be suppressed, then our trick might work. Okay, so that's the spirit of Stirling's approximation. So I think I'll just finish it in one line, then we'll take a break. So our factorial, our n factorial can be approximated by and exponential f of n is just a constant, so we can pull it out of the integral. And the rest of it is something that you're familiar with. It's just a Gaussian integral. We just derived, 3 minutes ago. And eventually it will give you something like this. Then you got the Stirling's approximation. So why this approximation is very nice is because you can just try to take an example, say n is something like 10 to the power of 23, and you just plug it inside. Then you see that the first term gives you something like 10 to the power of 23 times natural log 10 to the power of 23 is something of order 23. If I take the log to be, 10 based. And then you subtract 10 to the power of 23 and 1/2 natural logs something. But anyway, it is something of order 23. Then you'll see that, oh, this thing is basically irrelevant. We don't care about that. The most important thing basically come from the first two terms. So that's like the Stirling's approximation, and I think we'll take a 20-minute break now. And if you have questions, please ask me. So hi everyone. So I think we'll start today's lecture, and starting from the very confusing statement that a lot of you have asked me, and I found that it's probably due to the really bad notation. I'll try to think about how to correct that after the lecture and upload a better version of my lecture notes. But I'll just say what do I mean by a very specific example that we just discussed in the lecture. So let's consider the very specific example where our event space is just this these 6 numbers. Okay, you have the blue, you have the red 1, 13, and 8, and the blue 9, 7, and 273. Okay, so we have 6 elements. So what I'm trying to say here in this equation is that we are trying to ask the probability that we get the red character. Okay, so we can ask, what is the probability to get a red character in this special set? So it's quite easy because we only have 3 characters, 1, 13, and 8 are red. So the event number is basically 3, and the total number of events is 6. So we got 1/2. Okay. And then what do I mean by the right-hand side where we sum over B? So here, this B just means that we include all the possibility of being even number or odd number. So what I meant here is that if I try to evaluate the right-hand side of the equation using this specific example, the first the first joint probability will be the probability that we got the red and even number. Okay, so the probability that we got a red and even number is basically we only have this one event, character 8, right? So the first term of this sum will be 1/6. And the second term of this sum is the probability that we got a red and odd number. Okay, so in this particular set, the red and odd number are 1 and 13. So we got 2 events out of the 6 total events. So once you sum them over, then you got this result equal to the 1/2 probability that we got when we derived the expression at the very beginning. So it just means that when we sum over B, it just means that we don't care about the condition of B. We only care about whether it is red or blue. So you just sum over the even or the odd component. And and I need to say sorry that this is really confusing when I'm saying that, and I realize that my notation is not very good, so I need to change that. Okay, so that's one thing. And another thing is about the derivation of Stirling's approximation. I think I forgot to write it down, but the important thing about this expression is that this way of trying to evaluate the integral by expanding that nearby the point that the first derivative equal to 0 is called the steepest descent method. Okay, so it is very useful when you try to evaluate the integral of this kind of form. However, it is not guaranteed that the error will be small. But in this particular case, you can see that the error is very likely to be small because we evaluate the second derivative. And what we found is that the coefficient of this the coefficient of the second order correction, which is the second derivative at that point, actually will give you a factor of 1/n. Okay, so this is like the special property of this particular integral. So when you make n large, because eventually the goal for our approximation is that we want to evaluate or approximate n factorial when n is large. Okay, so when n is large, you'll see that this 1/n factor will actually suppress the second order correction, which means that this correction will become smaller and smaller when the n is large. So that's good, because that means that there's a chance that we can approximate our integral using this method. However, if you are doing this using this steepest descent method for arbitrary f of x, not not this f of x with the parameter n that can go really large, then you might not be that lucky. For example, the second derivative of your second derivative of your function f nearby the x bar might be some c value, which is not going to be suppressed like in this case. So that's like something that I need to mention, and I forgot to mention the name of that method. That's basically the steepest descent. Okay, so we just derived the Stirling's approximation and use a very simple example to see like why this approximation is going to be good, and the correction like in the last term is basically not really important for our purpose. Okay, so I think I'll continue to another very interesting observation that's related to sets of independent random numbers. Okay, so what do I mean by that? It just means that we have random number f1, f2, to fn. That's a set of random numbers. Okay, so it's at this moment, it still looks quite abstract. What do I mean by that? So let me just try to say a few words. So imagine that these f are derived by some random process. For example, you just toss a coin or you just toss a dice or something. Okay, so the outcome could be random. And for if you do this, you toss your coins or dice for n times, you'll get one result. Let's label this result with 1 at the upper step. And you can do that again, toss it for n times. Then you will have k trials. Okay. So in principle, if you just generate these random numbers with the same physical system, for example, you just use the same coin or the same sets of dice, then the result that you got from the first column, for example, if it is a coin, then you should have the probability of being +1 or -1 with probability weight 1/2. Okay, so it means that you have equal probability to get heads or tail. So if it is the same physical system, then for the second variable, it will also be true, described by the same probability distribution function. Any questions? No. However, in the mathematical sense, what we are going to derive actually can be relatively general. That you can say that the first element is always generated by some probability distribution function, like this binary distribution function, or it can be generated by some kind of Gaussian with random distribution for the second variable. So it can be generated from different probability distribution function according to your setting. But that's just try to know that mathematically it can be generalized. But in the physical system, usually we talk about the same distribution function with the same mean and the same variance of our distribution. Okay, so now we are trying to get the sum of these random variables. Okay, so this sum is related to each realization of your experiment. So it goes with the label k. So what we want to ask is, what is the statistical property of this sum, like we did in the random walk example, and you will be related to the average of these random variables. And because we know the average process is basically a linear operator, so we have this. And this is just the mean value. Okay, so the mean of this sum of random variables is just the mean of each random variables according to some of the distribution function. And if, as I mentioned, usually when we talk about the random variables, they are realized by a specific physical system. So there's no reason that why f1 and f2 have different means. Then this part can be simplified by this expression. Here it's like okay. So this is the sum, and now we should be very familiar with the variance. So the variance of this object can be evaluated. Oops. Directly. So here I just expand these squares and express the square of the mean, the most general sense. Okay. Now I'm going to just divide the sum into two parts, because now at this point this sum is all possible pairs of j and k. So I just divide it into this way. So again, this is a do nothing approximation. Not approximation, this is exact, sorry. I just rewrite things. Okay. So we just divide the k into the case that k equal to j and k is not equal to j. Okay. So we lose nothing. And this case, actually, we can simplify it, because when k equal to j, it just be fj squared. Okay. So now we are going to use the fact that we assume these fj's are independent. When we say it is independent, it just means that these pairs actually can be written as like this. Okay. So if we try to, let me try to write another line so that we know what's going on. So this term is just the last term. I just grab it here. And I just keep the fj square untouched. So you can see that yeah, just a tiny difference. Basically, there's just one term that's different, because when k is not equal to j, what is contained here will be killed by what is contained in the second bracket. When k is equal to j, there's no such term in the first parenthesis, but there are several terms in the second parenthesis. So wait, I think I made the mistake. Hold on a second. Here should be a plus sign, because I just divide my sum into k not equal to j and k equal to j. And here should be a plus sign. Okay. So we just get this expression. Okay. So this term came from the missing term of these two summation. Okay. and this is just the summation over the variance of these random variables. Again, if we assume that these random variables are generated from the same physical system, that means that these sigma j's should be equal with each other. So we can assume that, then we got the expression n sigma squared. Okay. So that's good. That means that we successfully derived the variance of our system. And let me just try to summarize what we just got. So the mean is just the mean of our random variable, but times n. And the variance is just the variance is just n sigma squared. Okay. So now we can define the relative standard deviation. It's basically the ratio between the standard deviation with respect to the mean value. And it makes sense to compare these two quantities, because the mean value just tells you that what's the mean, and standard deviation just tells you that your results might have some random fluctuation, and how far away this random fluctuation is away from your mean value. Okay. And what you have found is that we just plug in what we have. So we got something like this. Okay. So it is related to two things. One is the number of random variables, and also related to the property of your distribution function, basically the ratio between the variance with the mean value. So it's the also the relative standard deviation for this specific distribution function of our random number generating function. Okay. So this is one important result because the system that we care about at macroscopic world actually correspond to the case that the number of random variable is of the order 10 to the power of 23. So if you put that in, you'll find that the relative standard deviation is about the order. Let me call it delta relative. Delta relative is about the order of 10 to the power of minus 11 or something. Okay. So it means that the variance is very, very small compared with the mean value. So that's the magic of the large number. So what it means is that you might have, different trials when you are trying to evaluate your statistical property, and you'll find there's a mean value. It's this Sn. And the fluctuation, because of the random behavior, actually will give you something like that. But what we are telling you is that the ratio of this fluctuation is characterized by the sigma Sn. And this ratio of sigma Sn and the mean value is of this order if the particle number or your random number is huge, like to the 10 to the power of 23. So it means that this drawing is actually exaggerated picture, actually what you can observe is something like there's almost no noise. It's just like a flat line because the fluctuation is just so tiny. Okay. So so this is probably one of the most important results of probability theory for statistical mechanics. For some reason, let me write it down. The result is important because when n is 10 to the power of 23, the fluctuation is barely noticeable because the ratio is going to be ordered like 10 to the power of 11. And the second thing is that we only require the mean and variance to be well defined. Okay, but that's like a very general assumption that we made, and in most of the time, this assumption is a good assumption. So that's why statistical mechanics is really powerful, because it captures a lot of the situation where the probability distribution of a physical variable has a well-defined mean and well-defined variance. Okay. And I think this is a very good example that is controllable, and we can observe that why when n goes to be infinite, actually simplifies our problem. Okay. So naively, remember the motivation part, I said that there's a obstacle. When we are dealing with 10 to the power of 23 particles, basically we are doomed because there's no way that we can track every details of our system. So what we have observed in these simple examples, or like in the past two lectures, we see that actually when n goes to infinite, or when n is really large, actually it can help us to simplify our result. And here we can see that how we simplify our result is that it suppresses the fluctuation of our physical observables, such that actually when n is large, it is possible to have some regular physical behavior. Because if it does not have this property, then it is very likely that we are not able to solve the problem with n goes to 10 to the power of 23. Okay, so that's the meaning of the last few lecture. And there will be a homework about the central limit theorem, but I'm not going to talk about that too much at this moment. But I just want to motivate like why we talk about statistics and what we have done here. So, or like I would just want to mention two important factor or the spirit of statistical mechanics. Okay, so in the past two few lectures, I think I probably give you enough examples to show the first point. When degrees of freedom is huge, actually I can suppress the relative deviations. And the second part is the logical jump that we are going to talk in the next few weeks. Is that but actually this logical jump is more like a postulate that usually we think of our microscopic world as it is described by deterministic laws of physics. Okay, examples including Newtonian mechanics, quantum mechanics, and electrodynamics. Okay, those are deterministic physics. For example, Newtonian mechanics, we have the equation of motion F equal to ma. And quantum mechanics, we got the Schrödinger equation. Once you give me the wave function, I tell you how it evolves as a function of time. And electrodynamics, similarly, you give me the vector potentials, and I'll tell you how it evolved as a function of time according to the Maxwell's equation. So everything is deterministic. However, what statistical mechanics is trying to make the logical jump is that it postulates that when the degrees of freedom is so huge that we have all microscopic components interact with each other in a pretty much chaotic way, then maybe there's a very good approximation that we can make is that we basically give up the deterministic understanding of our system, but maybe we can describe our system using some probabilistic description. Okay, so that's basically a very big assumption behind statistical mechanics. But this big assumption actually tells us that the precise knowledge of the molecules in the microscopic world is actually not essential to understand the system as a whole. Okay, so that's the second big assumption of statistical mechanics. So in the next few lectures, I'll basically focus on this part. Okay, so I think today we finished what I want to say about the logical structure. So, but let me just give you a teaser about what we are going to talk about in the next few weeks. So we start from a very controllable microscopic model, basically random walks in 1D and 2D, and everything is exact. Then we said that, okay, we can try to generalize it to a random process where the random walk step size is not fixed. And then we derive the macroscopic expression for it and also connect it with some of the statistical property. And we found that even though we abandon the exact softness when we change the step size, but we can still get the macroscopic description such as diffusion equation. And we learn how to solve the diffusion equation by the Fourier method and the Green's function. And once we got the solution of the diffusion equation, we found that this macroscopic physics actually captures something related to the microscopic physics by seeing that the solution of our diffusion equation is a Gaussian wave function, and we can evaluate the deviation for that solution. And we found that deviation also gives us some root mean square proportional to square root n behavior. And that suggests the universality behavior for this kind of random process. Okay. And then we also say this one of the key ingredients such that we are able to reach this conclusion is that we are considering the case where n is really large, as we have many steps, or in other language that we have enough step size such that we can see the regularity emerges. Okay. Then if we think about what's the meaning of this process is, as I mentioned, it just means that we start from a very, to some extent, oversimplified model and see how it goes from its initial condition and reaches equilibrium. And that process is highly non-trivial, but in this simple model, we can derive it and understand that. So in the next lectures, or in the next maybe 2 or 3 weeks, we'll assume that we know how the system reaches equilibrium, and we ask what kind of property we can say at the equilibrium site. And that's basically the goal of thermodynamics. and we'll try to give a review about thermodynamics. And starting from there, we'll see how the concept of statistics kicks in and how it is connected with the thermodynamics. So I think that's today's lecture. So if you have any question, you can ask me. And if not, I think we'll end our lecture 10 minutes earlier. And I'll post the homeworks. So you can try to do the homework starting from maybe today or tomorrow. And remember, like today's lecture, there are some mathematical details that maybe I'm not doing it very well about the definition of events. I hope that you can try to go through the probability understanding, because eventually it will be a key ingredient for our future courses. Okay, so that's it, and see you next week.